And whenever it says SO substitution, you need to know what the SO group is. Can you see my screen?
Yes, I can.
So usually when you have an R group and a carbono group, that part is what we call SO group. We talked about Fedorcraft tessellation.
Yeah.
So the thing on the SO group can be replaced, but you don't want to replace a carbon or a hydrogen. Those ones cannot be replaced. So here you are thinking of Z to be an OH, maybe NR2 group, maybe a halogen, or even an OR group in anhydrides.
Okay.
Yeah, those ones can be replaced. But you cannot do that, say, with ketone, cannot be replaced. Aldehyde, this cannot be kicked out. Those are poor leaving groups.
Okay.
That's why they cannot be replaced. And these are the many mechanisms you are talking about.
Yeah.
Those are the living groups. So generally you want a nucleophile. This is not full mechanism. You want a nucleophile kicking out the Z. The living group to be lost. And that is what you are talking about, nucleophilic as SO substitution.
Okay.
Like I said, that was not a complete mechanism. Even the one shown down here is not complete mechanism. Only that we are saying once you attack, the carbon and the carbon opens up, you get what we call a tetrahedral intermediate.
Okay.
You have to go through, you'll see most of these mechanisms. Remember how I was saying PAD, then I said that's halfway.
Yeah.
So the tetrahedral intermediate will be the halfway. And then once it collapses down, that's when the living group leaves. So that's arrow 3, that's arrow 4. Very important. And this will make the mechanisms easier. Once you know that you have to collapse back the tetrahedral intermediate or you want to form it, then you kind of know how to go about this.
So the main goal of all of the ACL substitutions is to get rid of the leaving group.
Yeah, and you have to get through you must go through the tetrahedral intermediate.
Okay.
What is this young girl cooking? It's getting through my nose. I'm hungry.
Sorry.
It's okay. I think she came from school and she decided to cook. I think that smells like shrimp.
Oh, I love shrimp.
So now, let me know when you're ready.
I'm ready.
I don't want to take you too fast on this,
Okay. Yeah,
because
my brain's a little slow.
I noticed.
Oh.
I told you I know you better than you.
Okay.
So who is the electrophile? Who is the nucleophile?
The electrophile is the CO and the MEO.
You are so wrong.
Oh.
Electrophile is the whole A ring. The nucleophile will be B. This is the leaving group and this is your
Gonna
product.
attack the carbonyl element.
You are trying to tell me that Cl is the living group. That's what you're telling me. But the electrophile is characterized by a partial positive charge or full positive charge. And you know when you have a carbonyl group, we talked about this, dipole moments will make the carbon to be positively charged.
Okay, so
I don't know if he told you that.
no.
Then he will when you get to these slides, hopefully.
And then the MEO is the nucleophile. I was writing
That
that.
will be our nucleophile, and you have to show a lone pair and use that to attack. And that's what you're seeing as step one. So step one is going to be an A step only when you're starting with your most reactive derivative. So it's important we note that. I told you why this is the most reactive, because it has the best leaving group. So when you have anhydride or isochloride, you don't need to start with the P step. You will start with P step if you're dealing with carboxylic acid, if you're dealing with amides. Esters, it depends whether you're doing acid catalyzed or base catalyzed.
Okay.
But for sure, anhydrides and isochlorides will not start with a P step. They will start with an addition step. So you're adding, you're attacking, because that carbon I told you is,
Positive.
thank you, and the nucleophile is negative. Opposite charges attract. The best way I push my arrow is underneath, just to give the impression of an attack.
Okay.
And guess what we have here? What did
Carboxylate.
No.
No?
Carboxylate is when you still have the carbonyl group.
I don't know what that's called.
Hint, that carbon right there was sp2.
Oh, the tetrahedral intermediate.
Thank you. This is sp3. I told you your expectation of having a tetrahedral intermediate will greatly help you.
Okay.
Now, once you have the tetrahedral intermediate, then we can collapse it down.
Okay.
Okay, which is what's happening down here.
Okay.
You're collapsing it down because you have a leaving group. OCH3 generally is not a good leaving group, but in basic medium, it will leave. Good leaving, well, we are not losing OCH3. So I take that back. OCH3 will not leave here because the better leaving group is a Cl. Because if you lose OCH3 right now, it leaves as a strong base. You remember we used that for E2.
Yeah.
Good leaving groups leave as weak bases. Cl minus is a weak base. So that's how the tetrahedral intermediate knows it's the Cl that's gonna leave.
They leave as weak bases, you said?
Yeah, you know it's a weak base because if you protonate it, you get a strong acid. I know general chemistry didn't like you, but weak bases are usually part of strong acids. Strong bases are part of weak acids. Alcohols are weak acids. HCl is a strong acid.
Okay.
That's how quickly you can tell if you have a weak base. If the weak base gets protonated to give you a strong acid, if the species, the anion gets protonated to give you a strong acid, that anion was a weak base. If
Okay.
the anion like OMe minus gets protonated to give you a weak acid, that anion was a strong base. Good
Okay.
leaving groups must fall off as weak bases. They are stabilized that way.
Okay.
So we get this structure right here. That is an ester. So generally we have moved from the acid halide and added an alkoxide to give us an ester.
Okay. Okay.
All right.
Yeah, I'm good.
Okay, don't mind this. This is a different class I was doing. So, okay, going back there, by the way, we went from A to E. Elimination reactions forms double bond. And I call this elimination because we eliminated the chloride.
Okay.
So this process from acid halide to an ester is an AE mechanism.
Got it.
Not bad.
Nah.
Um, uh, I told you
So
this chapter. Go ahead.
when it's reacting with a strong nucleophile, I'm always gonna get an ester as my product.
Not always.
Okay.
It depends on the, I'll show you here, I know it's coming. It depends on the strong nucleophile.
Okay.
So
So
right,
both would.
yeah, so if you have an O nucleophile, yes, you're going to get an ester. How about if you have an N nucleophile?
Doesn't that not?
So let me say NH2 minus like sodium amide. You're still gonna go AE, but you get a different derivative, which is an amide.
Okay.
You can even have an anhydride from this. I'm just taking you a little bit forward.
Is this chapter easier than the aldehydes and ketones?
Yeah, it should be.
Okay, because it's already seeming a lot better.
Yeah, it should be. All these with negatively charged nucleophiles are AE mechanisms. Now, if they are neutral nucleophiles, it will be AED
Okay.
because you'll finish, for example, here, if you're adding ammonia, yet you're supposed to just end up adding NH2. Someone has to remove the extra hydrogen from ammonia. That is a D step.
Okay.
So down here, what you're getting is an anhydride. I did not draw the right product. Here you're getting anhydride. So you not always get an ester, even though we take anhydrides to be mixed esters.
Okay.
This is the maze of reactions which afterwards he should give you, starting with a given carboxylic acid functional group, making other carboxylic acid derivatives.
Okay.
And also synthesis will want you to think this way.
Ugh. Okay.
All right,
And
so are you good with that?
yeah, I'm assuming the reactions I learned from aldehydes and ketones can be mixed in with the reactions I'm going to learn from the carboxylic acids chapter, right?
It should be similar, only that you have living groups. It's telling you that it's not a one-step reaction. You know why? Because
Because
we
I
always form a tetrahedral intermediate. You have to go through the tetrahedral intermediate. There's no escaping.
okay.
Excuse my handwriting. I've been writing since morning,
Okay.
non-stop. All right. When you're ready, let me know. I've
Okay.
already gone ahead of myself, but you have the idea of what you'll be doing the rest of the session. So there's a reaction that we call Fischer esterification.
Mhm.
Other than using acid chloride, there's a reaction that we call Fischer esterification that can help make esters, but that same reaction breaks esters apart. Here you're looking at ester hydrolysis. A common situation is when a nucleophile is not strong enough to start the reaction, and also you don't have a good leaving group.
Okay.
So what do you need to force that reaction to happen? Acid conditions. So guess what will be the first step?
Protonate.
Thank you. When you have good leaving groups, you don't need to protonate. When you have a strong nucleophile, you don't need to protonate.
Okay.
There's a problem here. You have a poor leaving group and you have a weak nucleophile. So we need to assist this reaction to go. Then we are going to add acid catalyst. The acid catalyst will help us to do the P step. Now this becomes a very strong electrophile. Yes, you've not made the OR good leaving group, but now we have a strong electrophile that can be now attacked by the weak nucleophile. That is the reason why we protonate.
Okay. Oh, so the first step is to make the strong electrophile. Okay.
Yeah, because if you don't do that, thermodynamics, which is a chapter you don't like, I don't like too, but that's the only way we explain reactions. Let's assume we don't protonate. Let's assume we are so impatient, we are using our weak nucleophile to directly attack. You're going to get this guy, but look at its energy. You have
Oh,
very high activation energy.
so does that mean the product is like not really able to fully get made?
You're not gonna form your product. This thing is just gonna fall back down and kick the water out. You go back to your starting material.
Okay.
Which is why we protonate. When you protonate, the activation energy will be reduced.
Okay.
Your slides are very summarized, but I can tell what is the story behind them.
Okay.
So that is why. So once you protonate, then you are able to get to your product easier.
Okay.
Okay. Now see what happens after protonation.
This one's after protonation, the second one.
Yeah. So what happens? Very low activation energy. So if you start with a protonated ester, the activation energy is lower.
Okay, so you're gonna form product in this case.
Definitely, you're going to form your tetrahedral intermediate and you're going to go towards forming your product easier.
Okay.
And now, like I told you, your weak nucleophile is now very happy to attack now the activated carbonyl. when a carbonyl is protonated, we say it's activated.
Okay.
You see how there's no negative charge? Here there's a
Yeah.
negative charge. Here there's no negative charge. So this is a stable intermediate. Again, it was better for us to protonate to get the stable intermediate, tetrahedral intermediate, and then we can proceed.
Okay.
So I repeat myself in summary. When you have a poor leaving group and you have a weak nucleophile, you better protonate to activate the carbonyl so the reaction can go forward through a stable tetrahedral intermediate. In acidic conditions, you don't expect to have negative charges. So that's why this is wrong. You want to have only the positive ones. Ester hydrolysis, ester formation, both of them are acid catalyzed. The first step is a P step because you have a poor leaving group
Okay.
and you have a weak nucleophile. Does that make sense?
Yeah.
So now that gives us the basis on us doing the reactions later on. We are coming there, we are just giving ourselves a foundation. Now, what did I tell you when you have a strong nucleophile? Do we do a P step?
No.
Whenever you're given a reaction with a strong nucleophile, it's an easy mechanism. And in basic condition, you expect to have negative charges. You don't want to have positive charges.
Okay.
In strong base, negative charge expected in an intermediate. And the reaction is favored because you have a low activation energy, low energy barrier. That's good. So you're simply attacking RO1, get the negative charge, and then you can kick out your leaving group.
Okay.
In basic conditions, negative charges are expected. In acidic condition, positive charges are expected, negative charges are not expected.
Okay. So this is only when you have a strong nucleophile.
Correct.
So I know I messed up if I have a strong nucleophile and a positive charge.
Thank you. Now, when you have a weak base, expect to have both negative and positive. A weak base like ammonia, not water, expect to have negative and positive because the negative charge on the oxygen is compatible with the positive charge on nitrogen. Lewis structure rules. You want the negative charge on the most electronegative element, positive charge on the least electronegative element. Unlike up here when you attack with water, it's still a weak base. Where is it? Up here. It's a weak base, weak nucleophile. Without protonation, you get O minus and you get O plus. That's not compatible.
Okay.
One of them should be able to hold the positive charge better. The other one should be able to hold the negative charge better, which is why we needed protonation in that case. Here, you don't need protonation as a P step, even though we don't have a strong nucleophile,
Okay.
because O minus and N plus good, are compatible charge location. Rules, 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 rules. We just started.
I know, this is a lot.
we'll keep on referring to these rules as we go with our mechanism. So you kind of expect what's the next step, expect what's the next step based on whether you have a nucleophile, strong nucleophile, strong base, weak nucleophile.
Okay.
Yeah, that will be guiding us. You know, if you're adding something like a grignard to this ester, you don't need protonation. That's a very strong nucleophile.
Okay.
Yeah. You start with an A step, then E step, then you go from there. Now this is showing you the intermediate, how they collapse. You'd rather lose the OMe than the OH in this case.
Okay.
So the negatively charged tetrahedral intermediate in presence of a strong nucleophile, we say, is sufficiently reactive so that the alkoxide becomes a good leaving group.
Okay.
Let me show you what preceded this so that it will make sense to you. We are still talking about ester hydrolysis, breaking down of an ester using water, elements of water. So if you have OH minus, which came from sodium hydroxide, I like attacking from underneath, and I strongly suggest to you that that's what you should be doing in your mechanisms. So you'll expect the product, well, the intermediate. So that's what's happening. Your ester is converted to a carboxylic acid, and later on I'll tell you this does not stop, because that's an acid. In presence of this base,
Mhm.
you get a carboxylate at the end. Enzymes in biochemistry do this all the time using the aspartate and histidine residues in the active site of the enzyme. We'll talk about that when that time comes. Because the histidine amino acid in the active site has a basic nitrogen that pulls out the hydrogen from the aspartate. Otherwise, the complex will be so unstable and thermodynamically unstable, and the enzyme will stop working.
Got it.
Okay, so the neutral tetrahedral intermediate under acidic condition is not sufficiently reactive to dispel alkoxide leaving group. So this is what you're talking about. If you're in acidic conditions, don't expect to have O minus. Again, I'll take you back to where we started, or where this starts. So imagine you have an ester, you're in acidic conditions, you get OMe, and then from here, you would attack this molecule with OH, with water. Basically, you're in acidic conditions.
Okay. So what it means by it won't dispel the alkoxide. Does that the alkoxide is the OMe, right?
Correct.
So the OMe basically needs to be protonated in order for this to
Thank you. That's all they are saying
get
here.
water. Like
Mm-hmm.
you know how water has to get protonated in order, or
Correct.
alcohol has to get protonated to water to leave. And
Alcohol has to be protonated to leave. The OMe has to be protonated to leave as an alcohol.
okay.
Let me see. My Alex is misbehaving here, but I don't need it for now. So basically, you started with an ester. We'll do this mechanism. Started with a P step, then went with an A step. You know what the next step will be? D step.
Okay.
This step will now deprotonate the water that attacked. Actually, that gets you to where the notes started. So the D step will get you there. deprotonation of the HO, the water plus. And then now if you really want to expel the OMe, you have to start again with a P step.
Okay. A PE.
Yeah. And then that one's gonna go E step because you're eliminating as you make a double bond.
Okay. And then in this case, that positive charge on the oxygen's okay to be the product.
No, we'll deprotonate that to get our carboxylic acid and
Oh, didn't finish
the
there.
methanol. So you will have hydrolyzed your ester
Okay.
all the way to carboxylic acid.
Okay. So all the like my expected products for all of these should be a carboxylic acid is what I'm gonna.
If you're hydrolyzing amide, hydrolyzing ester, hydrolyzing acid chloride, you'll always end up with the carboxylic acid or the carboxylate if you're in basic medium.
And then if we're reducing anything, we're getting rid of a carboxylic acid.
You'll get an alcohol.
Got it. I like this chapter better than aldehydes and ketones. I hate that chapter.
Yeah. This one, I told you ahead of time, the mechanisms are related. Especially if you know you are always forcing yourself to get to the tetrahedral intermediate, you can make up something.
Yeah.
So in acidic medium, you're going pad ped.
Okay. Okay.
You good?
Yes.
And these are reductions, but before I do that, let me see something. And this is a Grignard. I told you Grignard is a strong. So this is what you're telling me. If you're starting with acid chloride, you end up carboxylic acid, anhydride carboxylic acid, ester carboxylic acid, amide carboxylic acid, nitrile carboxylic acid. Now, if you're in basic medium, all of these will end up giving you carboxylate. So it's just either,
So under acidic conditions, we'll get the carboxylic acid, and under basic conditions, we'll get the carboxylate.
that's it.
What slide number is that one?
This is 26.
Okay.
I wanted to relate what we just talked about so that things becomes easier. And the highlighted parts, those are living groups. With the exception of the nitrile, I told you the nitrile is just an adopted kid in these functional groups. But it eventually gives you carboxylic acid, so it has been recently adopted as a carboxylic acid derivative, the nitrile.
Okay.
But the living group is going to be a nitrogen, technically. Leaves as an amine.
The nitrogen one that's not a good leaving group is NO2, whereas NH2 is a good one.
Oh, NO2 is a good living group. NH2 is the bad one because it's, unless you protonate the NH2 to NH3 plus. I'm just scrolling to see what's coming. Okay, so you see, I wanted to relate what we've learned. This is slide 28. When you're ready.
Yeah, I'm ready.
Okay, so we are breaking the ester apart. So generally, this is what you're doing. And it's acid catalyzed. Remember what I told you. It's pad, pid. I'll quiz you on this shortly.
And then this one is getting protonated because the OME is not a good leaving group.
Thank you. And you're in acidic conditions. Unless you're using a very strong nucleophile. because this H2O plus is really H2O. So H2O is a weak nucleophile, OMe is a weak leaving group. That's why we add acid to give us H2O plus.
Okay, so then the water that we're going to use in the attack step, that's
Uh,
technically a
it,
weak acid
it's a
instead,
weak
or?
it's a weak nucleophile, but now we have a strong electrophile. It's like saying two very weak guys are fighting. That's quite a boring fight. You'd rather have someone that is strong and someone that is weak, so you expect someone to be knocked out.
Okay, got it.
A fight between a weak guy and a weak guy, that fight is never ending. A fight between a strong guy and a strong guy, that fight is never ending.
Okay, got it.
You either want strong nucleophile, weak electrophile. Like if you start with the ester, which is a weak electrophile, and attack it with OH minus, which is what you'll see here. If you're attacking with OH minus, the nucleophile is strong, the electrophile is weak. That fight will go well.
Okay.
Here,
So
the
basically, one of them needs to be strong and one of them needs to be weak.
thank you.
Okay,
Strong is a problem.
okay,
Weak is a problem. We need one to lose.
okay,
So that's why we protonate to get a strong electrophile. And now our weak nucleophile will do the A step. You would call that attack or addition.
okay. Okay. I'm good with this.
And then once you form your tetrahedral intermediate, this guy, we have to notice that that's our tetrahedral intermediate. Actually, there are two of them. I wouldn't call this the tetrahedral intermediate because it's still protonated.
Is it the one by the leaving group step? The
This one is my tetrahedral intermediate, the neutral one. But I've seen people calling this TI1, TI2. I usually go for the neutral ones.
Okay.
So you see, once you get these species, then you can deprotonate. Then you can say you are halfway there. This is the most common mechanism, either the AE or this one. It's the most common mechanism you can expect to get in the test.
Okay.
Formation of the ester, hydrolysis of the ester, and the AE mechanisms.
Got it.
This is not formation of ester. This is ester breaking. I'll show you the mechanism, the opposite of this. You see how this is reversible?
Yeah.
So you already know how you can reverse the pad ped mechanism and make it work.
Okay.
So next, like you asked, OME is not a good living group, which is why we protonate. You always keep on bringing up your acid to do protonation. And then we can knock it off.
Okay. This is like the like imine and enamine
Stuff here,
mechanism.
yeah,
That's like the one I've mastered so far.
very relatable. But you'll notice one doesn't have an A. This one doesn't have an A in the pad pit. So once you protonate, then you kick out this part right here. becomes your leaving group. Because he has a plus charge, he needs electrons. Methanol lost, so I could as well write here plus methanol. And then this is an E step, we say, because it's elimination. And then you remove the extra hydrogen, as we said before.
Okay.
So yeah, the mechanism for sure went paired peak, if you'd call it that. So anytime you're doing ester hydrolysis, expect it to go PAD. In acidic medium though, in basic medium there's no protonation. In the lab, for me, I don't do the acidic conditions. I do the basic condition. It gives me 100% yield, 99.9999, sometimes everything.
Okay.
It's just easier to work with. Boil the stuff for 40-45 minutes in sodium hydroxide.
Mm-hmm.
And that's how people used to make their soap, the
Oh, really?
carboxylate. Yeah. So in basic conditions, you don't get the carboxylic acid, you get the carboxylate.
Yeah.
So imagine the R group being a very long chain.
Mm-hmm.
That is your bar soap.
Okay.
So you will take the ester from the thigh of a pig. Just take the pig leg.
Interesting.
Yeah. Take the pig leg and boil it. It has a lot of fat, right?
Mm-hmm.
That fat is glyceraldehyde. You'll see it down here. When you esterify this thing,
Mm-hmm.
triglyceride. So when you boil these in sodium hydroxide, our our grandfathers knew chemistry before us. You get these carboxylates, which basically are soap.
Interesting.
They just boil it in sodium hydroxide. It's very easy. For them, they call
Basically.
it caustic soda. And glycerol is not trashed. Glycerol is actually used as a coolant
Okay.
and a lubricant. So, you had a question?
No.
I'm on slide 27. So, when you have a strong nucleophile, you don't need to do the P step. Just do your A step. Get your, it's charged, I know, but we're just gonna lose, that's the only intermediate we have. So, we're going to call this our tetrahedral intermediate. That collapses in basic conditions. OMe becomes a good living group.
Okay.
You get a carboxylic acid that does not survive. So this is the E step. It goes through the D step, and then you get your carboxylate.
Okay. So this is an AED one.
Yeah, in basic condition, S hydrolysis.
So in basic conditions with a strong nucleophile.
Correct. Now, if you want the carboxylic acid, you will do a P step. Notice that these are not reversible. Oh, why did they put it reversible? That's a shame.
Not.
It's not reversible.
Got it.
It's supposed to be one way. They are suggesting that OH can leave as much as OR can leave. But with heating, that does not happen. So if you protonate in an acid, then you're going to get your carboxylic acid if you want to go that far.
Oh, so if I like used H3O plus,
Yeah, you can
need it
use
in
it.
it.
Yeah,
Okay. Oh,
acid.
because the basic conditions always end with the carboxylate.
Correct. Unless you want it to go to the carboxylic acid, and in that case, you'll go AED. P. P is optional. Okay, I'm just finding relatable slides so that, oh, that process, by the way, is called saponification, making of
Uh-huh.
soap. And that's why you see this H2O plus added here.
Okay, got it.
Otherwise, this is gonna end up on the carboxylate.
Okay. Okay, I'm all good. I like this chapter a million times better than the aldehydes and ketones.
The
I'm
added
actually,
and ketones was wild. This one is relatable, yeah. Um, I wanted to show you the esterification one. Maybe that would be in the second packet. I don't know why he started with hydrolysis before
yeah, I don't know what he's
Fischer.
gonna give us the slides for that, which is annoying, but
Yeah, there's no Fischer here. Anyway, you got the idea.
yeah.
Let me see what we skipped. Before we do the reductions, back to slide 22, let's do
Mhm.
some practice. You will practice the mechanisms later. Let's predict some products because that's the bulk of your points. No. Let's start with this. I have a lot to ask you, but let's start with this. One at a time, please. When you finish the first one, you let me know.
Okay. I did the first one.
Okay, I'll draw what the products are and count your carbons very well. See if you got it right or not. So I usually find the breaking point, which is this point.
Yeah.
That's the shortcut.
And that's the heat specifically is what breaks the bond of the ester,
Usually the
correct?
heat helps you, but it's a nucleophile after the tetrahedral intermediate.
Okay, got it.
Yeah, this thing is gonna give you It's acidic condition, so I expect to have all neutral, no negative charge. In fact, if there's any positive,
Mm-hmm.
it will have to be that of water.
Okay.
And then this at some point is going to be protonated. Collapse it. I should get an OH here, and the other part should give me an alcohol. It's an organic product, so you have to draw both.
Okay. So the H3O plus will attack where the carbonyl is, kick off the oxygen that's a part of the ester, right?
Yeah, so this
And
will
then,
be protonated,
yeah.
and then that's where your H2O of the hydronium will attack.
Okay. Okay.
And then it will be deprotonated later.
Yeah. Okay. That makes sense.
Basically, pad pad mechanism is followed. Then do number 2 and let me know.
I did number two.
So number 2, I'm basically losing my chlorine,
Mm-hmm.
and that's where my OH will stay. It's acidic conditions. It stays as a carboxyl group.
That's a good easy one. Okay, I finished the last one.
The last one, this one is gonna give you the carboxylic acid,
Mm-hmm.
but you are in basic conditions.
So you get a carboxylate.
That's the catch.
Okay.
Now, if this is sodium hydroxide, so you expect to have the Na plus counter ion.
Yeah, that's what I was gonna ask. Okay.
We keep going. I hope I'm not boring you with the examples.
No, you aren't. My brain's just like fried a little bit. It's okay. So this NH2 is a poor leaving group, correct?
NH2 is a poor leaving group. That's why we need acid conditions for it to leave as NH3 plus, which is a good leaving group.
Okay, I finished this one.
Okay, so I expect again to get a carboxylic acid.
Yeah.
Any other organic product? No, because the NH2 is gonna leave as NH4.
So if we did this under basic conditions, what would happen?
The reaction will not happen for the amide.
That's what
No
I thought.
reaction. Amides are weakly reactive there. Esters will do it, but the amide will not do it. Nitriles will do it, but the amide will not do it.
Got it.
That's why whoever created us, God created us, He put these amide bonds in our structures, knowing that these are less reactive. These humans will collapse if I don't give them the amide bonds. However, you have other enzymes that break the amide bonds,
Got it.
but it requires a lot of energy. Okay, one more. What will be the product for that?
That's a big one.
What functional group is that?
What version of what?
What functional group is that?
Anhydride?
Correct.
Okay, I finished.
So you can, that was fast. You can cut on either side. You get carboxylate. No, you're in acidic conditions. So
You got the carboxylic acid.
yeah, both of them will be carboxylic acids, two of them.
I feel like this is like I thought it was easy, but I think this is a question that would get a lot of people because there's two
Yeah,
carbonate.
you have to show both. Why is it not moving? Come on. Anyway, so next we'll talk about reductions when you're ready. Those were SO substitutions.
Okay, I'm ready.
Can sodium borohydride reduce esters?
No.
Therefore, they cannot also reduce carboxylic acids.
Yeah, it's just the Jones that will. Or what am I saying?
That would be
They are.
oxidation.
Yeah.
Lithium aluminum hydride will do it. There are other strong reducing reagents, but they're beyond your scope. So generally, if you have an ester and you have a reducing agent, usually the grandpa, some books will write it as LAH. Just know the cutting point.
Mhm.
He will give you an aldehyde. Does not stop there. He keeps going. He will give you an alkoxide, which is why you need H2O plus to get the alcohol. So we always go through the tetrahydrointermediate, yes, then form an aldehyde, yes, then go further.
Okay.
This is strong. This is mild. That's why there's no reduction for the carboxylic acid and for the ester.
Okay.
You good?
Yeah.
We go to examples. That's the only way to survive all this. Work, 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 no play.
Literally.
I'm not jealous. Well, for me, I've been doing chemistry so much that it never bores me. I can do it for 15, 20 hours. I don't care. But for
I
someone who's
care.
new to this, what did you say?
I said I care when I don't know how to do stuff. When you don't know how to do stuff, it sucks. Like I hate that learning phase. I just like when I like know what I'm doing.
Mm, I barely used to study biology. I I spent all my time in chemistry and physics and math.
I'd rather study orgo than anything. So everything else like, takes for like this is like once you get the momentum, it's like easy.
Yeah. Once you get
Also,
it, that's it. You
yeah.
just look at the molecule, see the answer. It's just it takes much brain cells when you study,
Mhm.
when you're learning the concept, but once it's ingrained,
You
it
know what you are.
stays. Yeah. So the first thing I expect to get is an aldehyde, but doesn't stop there. Goes to the alkoxide, doesn't stop there. If there's no H3O plus, it will stop at the alkoxide. So it goes to the benzyl alcohol. So you have the ring, the phenol ring, and then you have OH. Most students will forget that carbon. Cyclic ester is called a lactone. Oh, by the way, here you have another product. You have two products.
So does will this have a ring opening?
Yeah.
Okay, I did it.
Oh, so you're cutting here. Definitely goes through the aldehyde. More reduction. Now you add another hydrogen. We'll see the mechanism shortly. And here comes H2O plus. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let me see.
So will this use two equivalents of
No, it's on the same molecule. So not two equivalents, it's the same structure. Having a diol.
Okay.
Now, if you are doing, so this is Italian short for compare to. So suppose you are doing the other one where you have H3O plus. It will be the same thing, but you're gonna be left with a carboxylic acid on one side.
Mhm.
Usually you get carboxylic acid and alcohol, right?
Yeah.
Like what we did here. You have two products for ester hydrolysis. So I forgot to give you this example before, so I'm giving it to you. So if you're doing ester hydrolysis of a lactone, don't put two products. It's the same molecule that has the carboxylic acid part and the alcohol part. The more of these problems you do,
Hmm.
the better for you. The test will turn out easier.
I
But
hope.
those that are not studying yet, they're in
Oh my
big
God.
trouble. They don't know what's coming.
I've studied a lot and I feel like I still don't know anything.
Yeah, it's a tornado coming.
More than a tornado.
More than a tornado, a very huge curve that you've never seen.
Yeah, I'm not a fan.
So that's how you do that. Let me know if you're good with that.
Yeah, I think so.
So your reduction reaction follows a simple mechanism. When you're talking about lithium aluminum hydride, it's really a hydride, which is why I just keep showing, excuse me, I keep showing H. Any of these hydrogens, for example, this one, is a hydride. That's a strong base. So you don't start with a P step. Rules apply. Which is why you see they're starting from the bond. That hydrogen is taking those two electrons.
Okay. Oh, because bases love H's. Okay.
Any of those hydrogen is a hydride. That's why the reagent is called lithium aluminum hydride. This is a hydride reduction mechanism. Hydride is H minus, proton is H plus. Hydrides are strong bases. In fact, they're bases only. They're usually not nucleophiles, but in this case, we take an exception because it adds. So we attack the carbonyl that is partially positive. Where we started, I told you our foundation was the carbonyl is polarized. So we are always using a nucleophile attacking that carbon. Our nucleophile here is an hydride. You get a tetrahedral intermediate. I know it's charged, but there's no other one that's not charged. So this will be our tetrahedral intermediate that collapses back down in presence of a strong base. OMe becomes a good leaving group. Usually it's not. Question: does H leave? No. Does the R group containing carbon leave? No. So OMe has to leave, giving you an aldehyde intermediate that kept on showing the aldehyde intermediate. Usually it's difficult to measure one equivalent versus one equivalent of your reactant for lithium and aluminum hydride. It's either way below or an excess. Most of the time we like to use it as an excess to make sure everything reacts.
Got it.
So here you are bringing a second grandpa. Aldehydes are more reactive than esters anyway, so the aldehyde will not stay around. You get another tetrahedral intermediate, but this one does not collapse back down. Do you know why?
Um,
It doesn't have a leaving group. You are not going to lose hydrogen. You are not going to lose hydrogen. You are not going to lose the carbon.
okay.
So without leaving groups, then you finish with a P step. Otherwise, it will be an alkoxide. So the mechanism was an A step elimination step, another A step, then P step. So it's A, E, A, P. When you're reducing ester, reduction of esters to what? To alcohols. Yeah.
This is a lot.
Mm-hmm. It's a much of just practicing. Now,
Yes,
when you're
that
reducing carboxylic acid is a different story.
when you're what?
Reducing carboxylic acid
Okay.
is a different story because I told you the hydride is a base. So, and the carboxylic acid is an acid. Do you think we are going to attack the carbonyl? No. Priority will be acid-base reaction.
Okay.
So that is the first step. I don't know what to call this. I'll call this D.
Okay. So, okay.
Yes, you are going to reduce it to the alcohol at the end. We'll always get a primary alcohol at the end. But you don't start with an attack. Because you see what we did with ester, we started with an attack, addition. But carboxylic acid is acidic, hydride is basic. Priority will be to steal that hydrogen to give you the carboxylate. That is not an alcohol.
Okay.
Yeah, so you are taking out that hydrogen. You're going to lose it as the gas. And then this part is going to be left with three. This part, the Al is left with three hydrogens. The lithium is going to be the spectator. You get a lithium carboxylate. That is the first step of the reaction.
Okay.
Now, when you have the aluminum hydride and you have a negative charge in the oxygen, you expect complexation. This is the complex formed here. Good luck with mastering that.
Wait, I have to know how to do that.
I I don't remember the last time someone was asked to show this mechanism. It's a rare mechanism to be asked. Very, very extremely rare to be asked.
Okay.
But you see the ALH3 that was formed before, forming a complex. So at the same time, simultaneously, the oxygen takes the aluminum, the hydride is added to the carbonyl. So you're trying to make a bond. I don't like the way it's drawn, so I'm going just to attack the carbonyl now. So pi bond opens, you get this complex. The oxygen is still there. And now you can lose that almero complex as a leaving group.
Okay.
Quite strange.
Yeah.
Yeah, so the O minus goes in and the oxygen mero complex falls out.
Got it. Okay.
We get an aldehyde, and then from there the story is easier.
So, okay.
Hmm.
I have to study a lot.
Yeah,
I'm so overwhelmed.
that mero complex just falls off as aluminum oxide thing.
So, is there a way to like this is a really dumb question, but since it's likely that I'm not gonna have to show that section of the mechanism, how do you continue without showing that? You know what I mean? Because like,
Nah, there's no other way.
yeah, okay. Saying is like I'm less likely to be tested on the mechanism.
I wouldn't even look at this when I'm crunched on time. I would
Okay.
focus on the other guy, on the other mechanism. This one is extremely rare. It would be barbaric for him to test with such a mechanism because that complex thing,
Yeah, it's weird. No, me
that
gusta.
complex thing is not easy to align, especially whenever you don't have time. So the reduction of aldehyde is easy. Just add the hydrogen and then you protonate. This one is an AP step. This preceding step is an E step. This one I
Okay.
don't know what to call it. It seems like an A step, you're adding a hydrogen.
Yeah.
This one.
Okay.
At the same time, you're eliminating the preceding step. Okay, so anytime you have a carboxylic acid, expect just to have a primary alcohol.
Got it. Okay.
Let me quiz you on something here. Are you able to get the product?
I think I got it.
Okay, so if I start with the H2O plus, I know it's reversible.
Yeah, and the OME is gonna leave, right?
Correct. I'll get these two products. And then this one's gonna go one way. Well,
Okay. And then we're
he
gonna get the oh
forms
that
an aldehyde first,
okay.
but never stops.
Okay.
you get this alcohol, make sure to have that carbon.
Hmm. Okay.